So there is no bad or unsatisfied edge. So by doing that, it's equivalent to a vertex cover problem. If you know about it, vertex cover is a problem that we try to bad or so what?
Yeah, go on, please.
So vertex cover is a problem that we just try to delete the minimum number of edges in a graph that we have still a connected graph. So for remaining edges, this is equivalent to vertex cover, which means finding the minimum number of nodes to cover all edges. So now they can apply two approximation algorithms. So the idea is first to transfer the problem to vertex cover and apply it to approximation algorithm. So that is the only thing that I can discuss about that paper, because it's mostly on proofs and linear programming stuff. So I just skip that and let's bring another paper. So the next paper is the projected tensor power method for hypergraph committee recovery. So the goal of this paper is to committee recovery over hypergraphs. And in this paper, the author proposed a method called project tensor power methods for exact committee recovery in a hypergraph. The projected tensor power method is an optimization algorithm for solving complex mathematical problems, particularly those involving a high dimensional tensors. And this algorithm is applied to symmetric uniform hypergraph stochastic block models, which capture high order relation among multiple objects. The goal is to identify the commutative structure based on their random hypergraphs. So it means that just give them a random hypergraph. We don't know nothing about the hypergraph, how we can to find the commutative recovery of this hypergraph. So in the left figure that you can see, the color represent the communities. These communities are unknown to us. We try to find these communities. What we know in this problem is the communication between every nodes. And if you look at the right side of this image, you can see that we have two communities, and the observations are triangles, which we call hypergraphs. So in this paper, they are supposed to have n nodes that are divided by k equal size communities, and it only means that if you look at every triangle, you can see all of them has 3 nodes, so k is 3 here. So
one thing, Sina. So what's the difference between the two figures? Is a left figure showing the communities on the regular graph?
Yeah.
And the right just shows the communities on a hypergraph.
Yes.
And they assume there are n nodes, and they will form k equal size communities. That's their basic setting, right?
Yes.
Okay.
So in this paper, our observation is just identity matrix A, tensor A, and the paper aims to recover the underlying communities, which means uncovering groups or clusters of entities within a network or data set that share common characteristic. It's just a basic clustering work. And
how do they define the adjacency tensor?
Sorry, what?
How do they define the adjacency tensor?
Oh, it just for every node that they just like adjacency matrix, that every node in a graph has some neighbors. So It's just
Yeah,
like,
for tensor, you need to define the number of dimensions, right? Or the
yes,
number
yes,
of
yes.
modes. What's their mode? What's the number of the modes or dimensions?
Oh, I don't know exactly. We can see the paper right now, but I don't know exactly right now. So do you
Yeah,
want to?
probably you can keep going and now
Okay.
then we can see how
Okay.
they choose the JSON tensor.
And in this paper, they are using a statistical generative models, and these models only used to capture the underlying probability distribution of this data set.
Mhm.
So their work is based on other papers, which is they are just mentioning that, and these results are come from other papers. So they mentioned that in other papers, if the different nodes belong to the same community, so there exists a hypergraph with probability p. Otherwise, if it's not exist, it's a probability q, and define p as q as follows. And alpha and beta, based on my understanding, because they are not mentioning anything, I just thought that they should be some factors to somehow regularize, or keep the amount of these probabilities. I thought alpha and beta should be something like that. And they mentioned that in previous works, I alpha beta, if it is bigger than one, exact recovery is possible. So one of the questions that this paper try to uh, answer is how we can achieve exact recovery from the computational aspect. So they first, in a very high sense, they use first the MLE problem to solve that, and try to optimize that. But how it is, but in a very, I'm not going very in a detail on this paper. I'm not I honestly not understand it. I need more time to understand that. But to record the underlying communities, they use Emily, and the input of that is just that agency tensor that we discussed, and our output should be another tensor, which is shows the underlying communities. To solve this Emily problem, you often use optimization techniques to find parameters value that maximize the likelihood function. The optimization process that they use is non-convex polynomial optimization. They use tensor power method to recover or identify hidden communities. And what actually this the PTPM,
Stina, you need to explain what's their probabilistic
yeah, I
generative model.
yeah, I can't understand it honestly. That's why I want to ask you guys. After this paper, we can finish this conversation, and for next week, I focusing on some detail about this
Yeah,
paper.
maybe you can pull out that paper. Let me take a look.
Okay.
I got a sense. It feels like it's similar to the stochastic block model like long time ago.
Okay, here.
Must be some section. Who is the author?
Who is the author? This guy? I don't know.
I mean, can I take a look at author list?
Yeah, here.
Oh, okay. Yeah. Let us look at the section which describes the probabilistic generative model.
Okay, they.
No, I think you should go up.
Sorry, what?
Yeah, I think you should go up.
Yeah.
Go up. There should be some section. Go up. I mean, There should be some section introducing the probabilistic generative model.
Yeah, I can find it. Project principle. I think there should be something here.
Or rotation of preliminaries.
Isn't
Okay,
it?
this is a multilinear multiplication. Okay, and okay. Oh, can you scroll down a little bit? Okay. Scroll down a little bit. Then scroll down a little bit. Oh, this is just about tensor operation. And scroll up. Yeah, these are about tensor operations. Yeah, can we look at section 3? I mean, just scroll down. It said a random hypergraph is generated according to the symmetric DHSBM with parameters NDKPQ.
Yes.
Oh, okay. So you see the I1, I2 to ID, these are tensor element, right?
Yes.
So if H star I1 here,
Mm-hmm.
so H H represents the hidden partition of the N nodes into K equal size disjoint communities, right?
Mm-hmm. Yeah.
So HI1, I guess HI1 is just one hot encoding, indicating if it belongs to some particular community, right?
Yeah.
Just as like if I1, I2 until ID are belonging to the same community,
It's,
then with probability P, you're gonna see an edge, right?
yeah.
But edge is of size D.
Mm-hmm. Yeah.
Right? They only assume this hypergraph, each hyper edge is connecting D nodes, right?
Yes. That should be it.
Yeah, otherwise you cannot give a so-called adjacency tensor.
No, you can't. Yeah. You're right.
And then they use the tensor decomposition like approach to recover this H star.
Mm-hmm.
Okay. Can you scroll down a little bit? Okay. So this is more like CP. Can you scroll down a little bit? Okay. I mean, scroll up. If from the probabilistic definition, this is more like CP.
So what?
This is like CP decomposition. Can you scroll down a little bit? Because you can view this as like hidden representation of each node.
Okay.
And they're just saying like, okay, if they're elements product, then dot product with one is one, then you got some probability to see the hyper edge. Otherwise, or some probability to not seeing the hyper edge. So you want to recover those H. H are just the latent factors, but they're just one hot encodings.
Yeah, got it.
Yeah, I'm not sure like if it's a one hot encoding or oh no, it must be one hot encoding. Otherwise, you cannot see their inner their atomized product. Then dot product with one will be exactly one.
Got it.
Okay. Yeah, I think we can go back. Yeah, this is CP decomposition.
Okay. So, okay, and the algorithms just have two steps: the power step and projection step. The power step just involves taking tensor product of certain matrices or which is it is tensor. The power step is usually applied over the time, and the more iteration that we have a better understanding of informations. So this power step is just help us to improve our estimation in hidden communities, and the project.
Yeah. I mean, our iterations are commonly used approach for tensor decomposition.
Yeah, here in this algorithm. So, and the projection step is the projection is involve projecting the result obtained from power step into a specific space that we want to. So that is the only thing that I can understand from this paper. So the thing that I wanted now is just to finish this conversation because I think these papers are a little bit heavy on details and theory and this kind of and optimization. So if I can only focus for next week on two papers.
Which paper? Which paper you said is heavy?
No, not heavy. It's I mean, they have something that I don't know, so I need to learn about them.
Our paper?
Or what?
You mean the power paper you just mentioned, or
no.
You mean this one?
Yeah, the next paper.
Oh, okay. Yeah, I think we can summarize the previous version. The previous paper you just talked about. It's published in 2013 this year. SML.
Yes, it is 2023.
Yeah, I'm kind of surprised how this kind of paper can get in. Because this is just make some variants of power iterations for CP decomposition. That's it.
Oh,
nothing.
I don't know exactly.
Nothing surprising.
And also there's another paper here. If I can find it out. It is just that I don't know if I can find it out right now or not, but it is just using some heat kernel stuffs on graphs for message passing. So yeah, some of those papers are not very, the idea of that papers are not very new or interesting when they're still in ICML or NeurNIPS or ICLR, and yeah,
that's why I feel like surprising how can they get in, because this is just a CP decomposition, and the only difference is that okay, I need to make sure that your representation are not continuous, must be some kind of like one hot encoding, but you can do that by projection or by whatever, and then you need to prove something. All those framework follows this classical framework.
Oh, I got it. Yeah, and also I look at it, we can use in that paper that use heat kernel stuffs, we can use PageRank heat kernel if they are accepting this kind of paper. So, by
Oh,
using
one thing I saw that I think I get a sense about the definition of D-uniform hypergraph. I guess there's so-called D-uniform hypergraph just means the hyperedge are of size D.
yeah,
That's why you can see that they said okay, they have like adjacent tensor.
let it.
Okay, let us look at this. This one looks much more interesting.
in this
This
one.
nonlinear feature diffusion, yeah.
So can I present this and another paper on next week?
You feel like you are not.
Yeah, I need I need sometimes to a little bit go on in more
Okay.
detail. So it is honestly it's better in terms of learning, but on Monday.
Yeah. Why not you yeah, let's stop here today. You can just keep more look at more details about this paper. This paper looks like it's much more promising.
Yeah.
Interesting than those previous papers.
Yes, exactly. And also, yeah, sure.
And because we're interested in I mean those traditional topic like how do you propagate labels, how do you jointly classify labels on the nodes are not very interesting. And we're interested in how do you combine physics with graph structures. That's why when I say diffusion, I'm interested in. I also look at how to define the diffusion operators on hypergraphs.
Yeah. So if you're really interested in that, so I can read this paper and that paper that I sent it to you about 5-6 hours ago.
Yeah.
Discuss them on Monday if you want.
Yeah, please.
Sure,
yeah,
sure.
you can spend more time and details. Look at details of those papers.
Sure, absolutely.
Okay. Any other questions or not just me? I'm encouraging everyone to ask questions, not only me. Okay, everyone feels good. Okay, yeah. Then let's continue our seminar on next Wednesday, and later I will ask you guys to I'll ask you guys to give me some time slots for 1-versus-1 meetings weekly. Okay, see you.
Okay, bye-bye. Okay.